I hope you all are having a great time attending the 11th series of IEEE Symposium on Computer Applications and Industrial Electronics. My name is Ritvik Kapoor. I am a software engineering undergrad in my final year from Delhi Technological University, and today I am here to present my paper titled SAGA, a hybrid technique to handle imbalanced data in software defect prediction. Let's get started with the first section, Introduction. A defect is a condition in software product that does not allow it to perform required tasks in an intended fashion. In other words, it is a bug induced by programmer that causes the program to malfunction. The early identification of these defects is very important, as in the later stages they become costlier to correct and difficult to detect. Patches in later stages of software development lifecycle also hamper the quality and maintainability of software. Predictive models that identify defect-prone parts of software can be evolved from defect data and software metrics. AEEM, NASA, PROMIS, Relink, and SoftLab are some of the popular defect datasets available. There are a large number of software metrics available. They are broadly classified into product and process-based metrics. We have used different categories of product metrics in our research. The goal in software defect prediction is to accurately label the component classes as defect-prone or averse to defects. While studying the defect data, it has been found that most of the datasets are skewed with less number of buggy classes. If we train a model with goal of maximizing accuracy on such data, then the model can become biased towards predicting majority class, leading to improper model training. Now, to make sure that the imbalance does not affect our model, result metrics like ROC-AUC, G-mean, and balance are used with accuracy. Previously, many attempts have been made for handling imbalance problem. They can be broadly classified into four types. Data level approaches, which are focused on restructuring the training dataset in order to balance them. Oversampling and undersampling methods are the most common examples of this category. Algorithmic level approaches, which introduce modifications in the classification methods to improve their performance when classifying the minority class. Ensemble methods, which combine the estimation of a set of individual classifiers trained over the same data, are the third type of approach, and hybrid approach is a combination of the above mentioned three approaches. In this study, we have proposed a hybrid technique called SAGA. The name is derived from the first letters of constituent techniques as highlighted on the screen. SAGA is SMOTE plus AdaSS plus genetic algorithm. Later in this presentation, we will discuss each component and connection between them in detail. While performing experiments with SAGA for software defect prediction, we have tried to answer these two research questions. Question 1. Can we modify the AdaSS ensemble classifier and use it in conjunction with data sampling to develop an imbalanced learning technique that works well with the dual class defect data? Question 2. On the basis of reliable statistical tests, how does the proposed technique perform in comparison to ensemble classifiers that involve other data sampling strategies? Section 2. Background of the study. Predicting software defects is a central area of research in software engineering. Discussion around handling imbalance in software defect prediction has been happening for a long time. We still feel there is a scope of developing a model that can give better results. The concept of feature space partitioning is relatively unexplored in our domain, but ADAS ensemble is an algorithm that belongs to the same category. Its efficiency in handling imbalance has been proven by Lopez Gracia et al. In their 2017 study, Ensemble Classification for Imbalanced Data based on feature space partitioning and hybrid metaheuristics. Also, SMOTE has been giving good results and has been used in other hybrid techniques to sufficient degree of success. Section 3. Data. We have used 13 open source Java repositories for our experiments. These datasets are a part of Promise Data Repo collection. From table in right, we get a fair idea about the size of each dataset, the number of classes in each dataset, and the percentage of classes that belong to defect category. We can easily observe that the data is imbalanced. Section 4. Here we will talk about the experimental setup. We begin by data cleaning and feature extraction. Then, on this reduced dataset, we apply SMOTE to reduce the data imbalance. This reduced and rebalanced data is divided into training and testing sets. Then we apply the AdaSS ensemble algorithm, and the best value of its optimizable parameters is found using repetitive iterations of genetic algorithm. Now the performance of SAGA over various algorithms is measured using result metrics and consolidated using statistical techniques for comparison. This correlation-based feature selection, we measure the correlation of various features with the field to be predicted, which is the class being positive or negative for defect in our case. Now, all those features which have correlation greater than a threshold are allowed to remain while the rest are removed. The example shows remaining features for respective datasets. Now, the data with reduced features is rebalanced using synthetic minority oversampling techniques. SMOTE first selects a minority class instance at a random and find its k nearest minority class neighbors. The synthetic instance is then created by choosing one of the k nearest neighbors B at random and connecting A and B to form a line segment in the feature space. The synthetic instances are generated as a convex combination of the two chosen instances A and B. The AdaSS ensemble is trained on rebalanced dataset received after applying SMOTE. AdaSS is an algorithm based on feature space partitioning, so the first step in training phase is to divide the data set into H clusters, where H is an external variable. Here we can see in the example how data is divided into clusters. If the training data has two features, clustered is a square. If training data has three features, cluster is a cuboid, and so on. Now, on each cluster, we train an individual ensemble. For each point, we proceed by selecting a cluster by comparing the Euclidean distance of the point from centroid for each cluster. Now, after finalizing the cluster, we choose the corresponding ensemble to that cluster for predicting the class of the point in question. Each ensemble is comprised of three base classifiers, namely support vector machine, k-nearest neighbor, and neural network, and each of them is trained on the data cluster assigned to the ensemble. Then, while prediction, we use a weighted average of predictions given by each individual method. The AdaSS ensemble helps in handling imbalance by locally focusing on data samples and using an ensemble of training algorithms. The objective of using genetic algorithm is to find the optimum values for weights assigned to different techniques in ensemble and the dimensional limits. Each combination of these variables represents a unique solution to the optimization problem. In general, genetic algorithm we go through iterations of selection, mating, crossover, and mutation for different combinations of variables to be optimized. We begin with a set of individuals which is called population. Each individual is a solution to the problem we want to solve. An individual is characterized by a set of variables known as genes. Genes are joined into a string to form a chromosome, aka solution. The selection phase uses fitness function to select a set of number of fittest individuals for mating.
We have used a weighted sum of accuracy, G-mean, AUC, and balance as the fitness criteria. During the crossover phase, offspring are produced by combining the genes of both parents. In certain new offspring formed, some of the genes can be subjected to a mutation with a low random probability. This implies that some of the gene values are randomly modified. If sufficient number of generations have passed, we stop iterating and select the individual, giving the best result as a solution to our optimization problem. After finding optimally trained ADAS ensemble, we run it on testing data and record the values of result metrics. The metrics are chosen so that sufficient attention is paid to the predictive capabilities while keeping the problems due to data imbalance in check. Now, to give a brief description of each of these metrics, G-mean is the geometric mean of sensitivity and specificity. AUC ROC stands for area under the receiver operating characteristic curve. The ROC curve is a plot of sensitivity versus 1 minus specificity. Balance is a modified performance evaluator obtained from FPR, false positive rate, and precision. And finally, accuracy is simply total number of correct predictions upon total number of predictions.
Section 5, Results and Conclusion. In table 3 of the research paper, we have made 4 subplots of 13 by 6 to consolidate the result metrics from all the experiments. Each cell holds the value of a result metric obtained by using a technique on a dataset.
Research question 1. Can we modify the ADAS ensemble classifier and use it in conjunction with data sampling to develop an imbalanced learning technique that works well with the dual class defect data? From the results table mentioned in previous slide, it is to be noted that for SAGA, the range of AUC-ROC is 0.768 to 0.994. The range of G-mean is 0.729 to 0.949, and the range of balance is 0.728 to 0.95 over the chosen datasets. So it can be concluded that the proposed model has handled the problem sufficiently well.
Table 4 holds the results of Friedman test conducted for comparing performance of SAGA with and without using SMOTE with other techniques.
Research question 2. Based on standard evaluation metrics for classification problems, does a technique perform better than other popular ensemble classifiers using the various data sampling strategies? From Table 4, it is evident that SAGA has a considerable performance advantage over other techniques, and using data levels mode increases the performance margin of SAGA. SAGA had and first rank across averages for all the result metrics. Also, SAGA without SMOTE had second rank across averages of result metrics except G-mean, where it was overtaken by Easy Ensemble.
In conclusion, SAGA has demonstrated a tremendous improvement in all aspects of performance as compared to the methods currently being used. We have also analyzed the performance of boost provided by using SMOTE and proven that even without using it, the GA optimized modified ADAS ensemble has decent performance for binary classification and imbalance learning. Thank you for your time. The research was conducted under the supervision of Dr. Ruchika Malhotra, Computer Science Department, Delhi Technological University, by me, Ritvik Kapoor, Paridhi Saxena, and Parth Sharma. All of us are final year BTech students in Computer Science Department of Delhi Technological University.